Hello everyone. So we are back for this part of the lecture. I did say I wanted to go for an example just to see how what the practical implication of what we are doing really is. If you go back to the EAI case study, which is basically about a group of let me just see if I can get it from so that we get the full case study. It will have to be something. So just bear with me for a bit. So it's actually over here. So the EAI problem. So it's the electronics associate sampling problem. So in this particular case, you have this information. You have a director of personnel for who has been assigned the task of developing a profile for the company's 2,500 managers. So the population is actually 2,500. And using these 2,500 managers, he basically computes the population mean. This is the mean salary for the 2,500 managers, and the standard deviation is $4,000. So this is the information that we have here. But then the manager goes on to get a sample of 30, and then these are the values that you get for the sample of 30. These values over here. So if I just clear out this, this sheet, if I just clear out this Excel sheet, then we have this situation where you have. So this is what we have as our summary. We have the population. We have the population mean is $4,000. Then we have the population standard deviation. Actually, Excel, I think calls it STDevP. So we say the population standard deviation is actually going to be population standard deviation is $4,000. So that's actually standard deviation, and the population mean is 51,800. Yeah. So this one is 51,800, and then the sample. What we have as the sample mean salary is 51,814. So what we have as a sample mean is 51,814. It's 51. Sorry, it's actually here 51,814, and then we have 3348. 3348 as the sample is actually the sample stdev s. So we're basically saying, if I just go to Word for a bit, if you really want to get the sampling distribution now, if you want to get the standard deviation. Standard deviation for the sample distribution. Just a minute. I need to zoom in. Then maybe increase the font size. So if you want to get the standard deviation, if you look at the sampling distribution, which is actually a normal distribution. And remember, we said a normal distribution is defined by two things. The normal distribution is actually going to be defined by two things. So this is a normal distribution. This is a normal distribution. And remember, from previous chapter, I know that a normal distribution is defined by two things. That is the standard deviation and the mean. And we know, we refer to this. So we've been using this notation So this the expected value of x. So referring to this as x bar, yeah. So the expected value of I need an accent. So the expected value, which is written like that, for the so just a minute. I like to write this out, so you're going to bear with me for a bit. So the expected value for of the mean of the sampling distribution. So that is this value that we have over here. That is the value when you compute all the standard deviations for all the when you compute all the means for all when you compute all the means for all the possible samples, that's what we're talking about, yeah. So the expected value that we expect, the value that we expect to get for those means is actually going to be equal to the value, the mean of the population. It's actually going to be the mean of the population. So it's actually going to be equal to mu. Then the standard deviation, which is the standard deviation of the sampling distribution, which is going to be given by let me just insert a new equation here. So I like to actually write this out. So the standard so that's not the one I actually wanted. So let me just go back for a bit. So you're going to have to bear with me. I like to write this out. It's actually a very good practice to write this out. It helps you to remember. It helps you to remember these expressions. If you don't actually do write them out, unless you are some sort of genius, it's not really going to be easy for you. So you want to get the so the standard deviation of this, we said, is going to be just a minute. I just need to scroll a bit. So it's going to be, it's going to be equal to, so first of all you have to get the population correction factor in this situation. So population correction factor, we say is going to be sort of finite. Population correction factor is minus n, capital N minus n, and then you have capital N minus 1. So this actually the counts for and then you're going to multiply this by n over root sigma over root n. So you're going to multiply this by sigma over root n. So let me just get the fraction. So you need to have sigma. You need to have sigma, which is basically that. Then we need the radical over root n. So this is true for as long as this is true for as long as if n, so we need another fraction. So if so this is true if n over is equal to is less than or equal to 0.05. So let's first of all see what's going to happen, because here we have n is equal to 30. Then we have, sorry, that's the lowercase n. So this is the sample size is 30, and population size is 2,500. So let's see what value we do get. So that's going to be calc. If I do the calculator, that's going to be 30 divided by 2,500. This gives you point. So this is actually less, yeah. So this is actually less. So that means we do not need to apply the population correction factor. So it means that our sampling distributions, the samplings distributions standard deviation can simply be given by this. So we already know sigma is 4,000. 4,000, and we know that our n is 30. So if you do root n, what do we get? So root of 30, let me just do it over here. So so we want to do stdev the sampling distribution is actually going to be, so the standard deviation for the sampling distribution is actually going to be this standard deviation over here divided by the square root of 30, the square root of 30, and that will give you 730 as the actual standard deviation, right? So you could have a situation, for instance, if we have some value and we want to find out what is the probability that for instance, if you want to know the probability that this value that we get from our sample is within 500 of the actual mean, yeah, has got an error of plus or minus 500. So let's say you want to find out the probability that the value that we are going to get from the sample mean will actually have an error of plus or minus 500. So so that basically means if so this is our population mean over here, yeah. So an error of plus or minus 500 basically means that what is the probability that the mean that we get from any sample is going to be from this figure, which is 52,300, 52,300 to this figure. So let's see. So let's get back our mean. Let's see. So 51,300. So because we know that this is actually a standard, is a normal distribution, so it means we can actually compute the probability. You can actually compute the actual probability that the value lies within a specific range of values with some degree of confidence. So because this is a normal distribution, it means that all we need to do now is to compute the z values for these bounds. So we want to see a probability that the value lies within plus or minus 500 of the actual mean, yeah. Since we know the standard, so since we know the sampling distributions, since we know the sampling distribution standard deviation, it means we can now compute these values really easily. So remember, the sampling distribution standard deviation is this over here, yeah. So all you have to do is actually compute the z values. So the z value for this is going to be is basically the value minus mu. Remember, the z value is x minus mu over sigma. So the z value is going to be, I just need a new fraction. Just to remind you, so we need to compute the z values to convert this to a normal. Remember, our probability distribution is actually in our probability our cumulative probability table is actually as a standard normal distribution. So we need to convert this to a normal distribution by simply computing the z values. Remember, x value is actually this is how you get it, x minus mu over sigma. We do already know our x minus mu is 500 because we want it to be 500 either way. So it's basically 500 over sigma, and the sigma is the sigma x, right? Is this value over here, the 730? It is this 730 point. Just a minute. So this is our sigma over here. Let's see. Okay, it looks really tiny. 500 divided by 730.2967, yeah, 2967. And what does this really give us? So we have 500 divided by 730.296.7.68 0.68. Yeah, so it's basically 0.68. Of course, the other bound is actually minus, because it's simply what you're going to do is so the other bounds is going to be minus, because it's plus or minus. So it's going to be, so you want to have the value between 0.68 and minus 0.68. So if you go to our maybe I can clear this now. So if you go to our cumulative probability distribution, because we have the z values now. So it's just a minute. Oh, okay. So let's go back. I know it's like the second page. So let's see what happens. So if you go back to our cumulative probability tables, 0.68 is going to be 0.68 is actually here. So minus 0.68 is 0.2483. So that is 0.2483, 0.248. We should actually start with the positive one, the cumulative probability. So 0.68. So 0.68 is over here. So 0.68 is 0.7517. Yeah, this column 0.7517. So I'm taking a bit of time here, but then you have to get used to doing these time consuming things. 0.7157. So it is 0.7517. That's the cumulative probability. It is that, and we're going to minus the cumulative probability. Okay, just confirming that I'm doing the positive side. So minus the cumulative probability at 0.2483. So that's minus 0.2483. So this gives us the probability that our value actually lies within 500 of the mean. Let me see if this actually tallies with the book. Standard deviation. So just a minute. So that's actually our value that we did get for the standard deviation of the sampling distribution. Then back to the EI problem. Then so this is when he's actually so I think this is our computation, and they are deriving the values. So we get the z values. You can see the z values over here, similar to what we just got. Then the actual area under the curve. What value did we get for area under the curve? 0.5034. So you can see that actually our values are exactly the same as the values in the book. So we did talk about the impact. What would be the impact of actually changing? If you actually change the sample size, for instance, if instead of 30, we use a sample size of 100. If we do use a sample size of 100, that means that the actual that this sigma x, which is the standard deviation of the sampling distribution, is actually going to be, remember we already have this to be 4,000 for the population, and then this would be over root n. N is going to be 100, so this would actually be 10. Yeah, so this would give us the this would give us a sigma of 400. This would give us a sigma of 400. because you have 4,000 over root of 100. So if that is the case, then you have x minus mu again. Oh yes, it's not over 400, yeah? So x minus mu, we said, is 500. X minus mu is 500. So 500 over 400 is going to give us, so 500 divided by 400 is going to give us 1.25. So you have, the bounds are going to be 1.25. 1.25, and then to minus 1.25. Minus 1.25. So these are the z values. So if we get the cumulative now, if I go back to the the probability distribution tables, so just a minute. So minus 1.25. I've got to start with the positive side, I guess. So minus 1.25. So I'm only doing this because it's easier to arrange the values. So minus 1.2. So you have the 1.2 row, then 0.5 column, 0.8944. So we have 0.8944, and then we are going to subtract. The minus side, 1.25, that's going to give us 0.1056. Did I get that right? So just a minute. So let's see what happens. So you have 0.788, right? So the value is going to be 0.788. So our value, if you have n, when you have n is equal to 100, is actually going to give you 0.788. So let's just check with the book and see if that's what they actually do get when n is 100. Slowly. So just bear with me for a bit. So this is the previous standard deviation. So these are the previous probabilities. So this is what happens when you increase the sample size. You get a probability of 0.788. So this is actually correct, what we just did. So that basically means that if you have a bigger sample, you have a higher confidence that your value lies within certain. If you do define a certain bounds, yeah, the bigger the probability, the higher the bigger the sample, the higher the probability that your sample is within, that your point estimate is within those bounds. We could have done this with Excel as well. If I just go back to the previous example. So the previous example, we wanted to find the so you can actually use the Excel normdist function if you want to find the cumulative probability. But here in this case, we wanted to find a cumulative probability that the value lies between 1.25 and minus 1.25, or with a standard deviation of 4,000 and a mean of 51,000, because the mean actually remains 51,800. So you could have used the Excel function. This is faster, but of course I didn't want to show you this approach very quickly, because it's not going to be available for you in the exam. So the x is basically the cumulative value. So you want to find 1.25, then the mean is 51,800, and then the standard deviation was 400, and then the keyword true to mean that this is basically a cumulative probability distribution function. So it basically gives you, I think I need to format, so I want to format this as a fraction, as a number, so it's the normal distribution that the, okay, so that shouldn't be 1.25, it's 51, because the actual value that we do want is, you don't normalize at this point, so with Excel is, so I want to get the value, the cumulative probability for that is actually 52,300. So that is 52,300, right? So that's a cumulative probability up to this point, yeah? And we want to actually subtract. So let me just extend this formula. So we want to actually subtract the cumulative probability. So we want to subtract norm dist. So norm dist is basically normal distribution, right? Norm dist. Let me just put it uppercase. So we want to actually subtract norm dist. Just a minute. So 51,800. So 51,800 minus 500, because we're doing plus or minus 500. So that's 51,300. Then 51,800, the mean, then the standard deviation, and then the true keyword for cumulative. And this is the value that we actually did get previously when we used the probability, cumulative probability tables from page 2 and 3. So that is basically, the part I wanted to go through. Then let's take a break and then come back for the next section.